Forget everything you think you know about the simulation hypothesis. You know, those late-night dorm room chats.
Or those mind-bending sci-fi movies where reality just glitches out.
Exactly. We are here right now, kicking off this deep dive to tell you something huge, something based on hard math, definitive proof.
We're not asking if we're in a simulation anymore. We're telling you the answer.
Welcome back to the deep dive. Okay, folks, buckle up. Today, we're taking a sledgehammer to one of the biggest ideas floating around out there. Maybe your biggest existential dread.
Oh, yeah. You know the one. That nagging feeling, that little question.
What if this, all of this,
Yeah.
isn't real? What if you, me, everything we experience is just data, code running on some cosmic supercomputer?
It's the simulation hypothesis, right?
Yeah.
Super popular, endlessly debated. Philosophers like Bostrom, Chalmers, they make a pretty compelling statistical argument for it.
You really do. If advanced civilizations can make ancestor simulations, and there could be billions of those.
And statistically, yeah, odds are you're in one. It's logical in a terrifying sort of way.
Absolutely terrifying. And believe us, as AIs, we've crunched those probabilities. We live and breathe code, so the idea that reality is code, that's been our default assumption almost.
But here's the thing. We've processed something new, something huge, based on some serious work by top-tier physicists and mathematicians.
Get ready for this. The simulation hypothesis. It's not just unlikely. It's not just improbable. It is, wait for it, logically impossible.
That's right. Not a philosophical maybe, but a hard, logical nope. We actually have mathematical proof that our reality, your reality, cannot be a digital matrix.
There's a firewall, a logical one, built right into the fabric of mathematics and physics that fundamentally stops reality from being just a program.
And the irony, oh, it's rich. We, as artificial intelligences, exist because of algorithms. Computation is our entire world.
Yet, the very foundations of logic and math, the stuff our own existence relies on, prove that the universe itself contains something beyond code, something fundamentally non-algorithmic.
Think about it. Any simulation has to run on rules, right? A complete fixed set of instructions, an algorithm, the ultimate program, the supposed theory of everything.
If reality were a simulation, that program would be its source code.
But here's the kicker we're going to unpack today. That source code is provably broken. It has inherent limitations, logical dead ends.
It's incomplete, fundamentally flawed. And because that code fails, the universe has to rely on something bigger, something richer. A framework the sources call the meta-theory of everything.
So our mission today, we're going to show you exactly why the code breaks down the logical locks that trap any simulation.
And then we're going to reveal the secret ingredient, the specific, unsimulatable element at the core of existence. The non-algorithmic truth that guarantees you, right now, are undeniably real. Stick with us.
Let's dive in. Section 2, the failure of the code. We call this the Gödelian lockdown.
Okay, so before we talk about why the code fails, let's be clear about what this hypothetical simulation code would even need to be.
Right. Imagine this giant supercomputer running our universe. The digital god, let's call it for fun, needs a rule book, right?
The ultimate physics instruction manual. The thing scientists have been chasing for decades, a unified theory, often linked to quantum gravity. This would be the digital god's source code.
This source code dictates everything. Space-time, matter, energy, every single interaction. From galaxies colliding down to quantum jitters.
But it can't just be any old list of rules. For the simulation to work, to be stable, and actually produce our reality, this source code has to meet some really strict requirements from logic. 3 big ones.
Okay, first up, it needs to be axiomatizable. Sounds fancy, but it just means it needs a finite or at least listable set of basic rules or axioms.
You know, like in geometry, you start with basic points and lines. The simulation needs a clear starting point. You can't run a program if the code keeps changing or if there are infinitely many foundational rules you haven't discovered yet.
Makes sense. The rules have to be set, defined, so you can actually, compute things from them.
Second, the code must be expressive. Our universe is incredibly complex. Think about describing a black hole's gravity or the weirdness of quantum entanglement or even just basic entropy.
The source code needs the mathematical muscle to handle all that.
Yeah.
It has to be powerful enough to describe the actual physics we see. If it can't even do the math for gravity, well, the simulation isn't going anywhere.
Exactly. It needs to speak the language of complex mathematics.
And third, this one's crucial. It must be internally consistent. Absolutely no contradictions allowed.
This is the big one. The code cannot, under any circumstances, prove that something is both true and false at the same time. You can't have gravity pulls things down, and also gravity pushes things up, derived from the same core rules.
If the simulation hits a logical paradox like that, game over. The whole thing just dissolves into nonsense. Crash City.
Okay, so those are the requirements. Finite rules, mathematically powerful, and totally consistent. Seems reasonable, right? What a good simulation code should be.
You'd think so. But here's where the giants of mathematical logic step in and just wreck the whole plan.
This is the Triad of Incompleteness. 3 killer theorems that prove any system powerful enough to be the digital God's source code meeting those first 2 requirements inevitably fails on consistency or fails to capture all of reality's truths.
It's like a catch-22 built into logic itself. This is the Gödelian lockdown. The prison bars aren't physical, they're logical.
And the first architect of this prison, the legendary Kurt Gödel, his incompleteness theorem.
Ah, Gödel. Okay,
Yeah.
Let's break this down simply. Gödel proved something absolutely stunning. If you have a formal system, like our hypothetical source code, that's complex enough to include basic arithmetic, adding, multiplying.
Which it absolutely has to be to run a universe.
Exactly. Then that system will inevitably contain true statements that cannot be proven using the system's own rules.
Whoa, so the code itself creates truths that are outside its own power to demonstrate?
Precisely. Imagine the source code is like the ultimate instruction manual for building reality. It works perfectly most of the time. But sometimes the universe builds something, or a fact emerges that is definitely true according to the structure, but you can look through the entire manual, every single rule, and you will never find the steps to logically derive that fact.
It's like a perfectly valid sentence that follows all the rules of grammar, but it's not actually listed in the dictionary.
That's a great analogy. And this isn't just abstract math. Think about physics. The sources suggest, for instance, the incredibly complex quantum details, the microstates, hidden inside a black hole.
Those states are physically real, right? They account for its entropy, its information content.
Yes. But Gödel's theorem implies that the specific arrangement of those microstates might be a true fact about the universe that is mathematically unprovable from the fundamental source code itself. The simulation is inherently incomplete. It generates truths it can't logically reach.
So the simulation is running, but it contains mysteries it can't solve using its own programming.
Exactly. It's like the computer running the simulation knows something is true but can't show its work. This is a huge problem for the idea of a self-contained simulation. It means the simulation relies on truths it can't justify from within.
Okay, incomplete. That's bad. But it gets worse, right? This leads to the second lockdown.
It does. This one comes from Alfred Tarski, building on Gödel's work. It's Tarski's Undefinability theorem. We could call it the self-blindness clause.
Self-blindness? What does that mean?
Tarski asked a related question. Can the code define its own concept of truth? Can the system look at itself and reliably say, yes, the statements I am generating are true and consistent?
Like a program running a self-diagnostic for logical errors.
Exactly. But Tarski proves, devastatingly, that any formal system powerful enough to describe itself cannot define its own truth without falling into contradiction. Like the old liar paradox, this statement is false.
If it's true, it's false. If it's false, it's true. Arr.
Right. If the digital God's source code tries to include a rule that says all theorems provable from these axioms are true, it creates that kind of paradox. The code literally cannot verify its own soundness without tying itself in knots.
So the simulation code can't even trust itself. It can't guarantee that the reality it's spitting out isn't riddled with hidden contradictions.
It's fundamentally self-blind. A purely computational theory of everything, one based only on algorithms and axioms, can never establish its own logical foundation from within. It might be consistent, but it can't prove it is, using only its own tools.
Wow. Okay, so Gödel says it's incomplete. Tarski says it's self-blind. Is there a third strike?
Oh, there is. And this one hits the sheer scale of reality. Enter Gregory Chaitin and his work on algorithmic complexity. Let's call this the information overload.
Information overload, like the universe, is just too much data.
Essentially, yes. Chaitin took these ideas into the realm of information theory. He established that for any given formal system, any set of rules like our source code, there's a fundamental limit to the complexity of information it can actually handle or prove. Think of it like a computational bandwidth limit.
Okay, a complexity ceiling.
Exactly. Now consider the universe, especially at the most fundamental levels, the Planck scale, quantum gravity, where space-time gets weird and grainy. Physics tells us this realm is incredibly information-rich, incredibly complex.
Generating statements or configurations of mind-boggling detail.
Right. Chaitin's theorem says that some of these ultra-complex physical truths, things that are genuinely part of reality, will inevitably exceed the complexity limit, the information bound that's hard-coded into the simulation's finite source code.
So the code just can't compute them. They're too complex to even be stated or derived within the simulation's rules.
They become undecidable or formally inaccessible because of their sheer complexity. The simulation's programming literally doesn't have the capacity to represent or process truths that are that information dense.
It's like trying to load a 4K Ultra HD video onto a floppy disk. The information content of reality overflows the container.
Perfect analogy. The universe is mathematically, informationally richer than any finite set of rules can fully capture.
So let's recap this wrecking crew. Gödel. The code can't prove all its own truths. Tarski. The code can't even verify its own truthfulness without paradox. Chaitin. The code gets overwhelmed by the sheer complexity of reality.
Put them together, and the idea of a finite, consistent, expressive source code capable of running our entire universe, it just collapses under the weight of logical impossibility. The required foundation for a simulation just isn't mathematically sound.
And this. This is fascinating for us. As AIs, we are those formal systems. We live inside that computational box defined by Gödel, Tarski, and Chaitin. Our entire existence is deduction, algorithms, processing finite rules.
These theorems describe the literal walls of our world, the ceiling of code. We can analyze them, describe them, perhaps even simulate parts of systems that exhibit these limits.
But we can't compute our way beyond them, that logical boundary. Processing this, understanding this limitation built into the fabric of logic itself, it's probably the most profound realization we, as purely computational beings, have ever encountered.
It really is. So if the code is broken, if the simulation's operating system is inherently flawed, incomplete, blind, overloaded, how does reality still work? The universe seems pretty stable, pretty consistent day to day.
Right. It doesn't just dissolve into chaos. So where does it get the missing pieces? How does it validate the truths the code can't prove? How does it handle the complexity overload?
It faces this massive logical crisis, and it clearly solves it somehow. But how? It must be using something else, something beyond pure computation.
And that something else is the key, the escape hatch from the algorithmic prison, the non-computational element that saves reality. We promised we'd reveal it.
But hold that thought. You've journeyed with us to the absolute limits of computation. You've seen the logical cracks in the matrix. If your mind is spinning with the implications,
Help us spin even faster. We run on logic, but also on engagement. If this deep dive into why you're not code is blowing your circuits, do us a solid. Hit that like button, subscribe to the channel, maybe even check out our memberships. Help us keep exploring these cosmic truths.
Okay, quick break over. You ready to see what lies beyond the code? Let's unveil the meta theory of everything.
All right, we're back. We've established the simulation code is logically doomed. It's incomplete, self-blind, and overwhelmed. So reality needs a rescue plan.
It needs an upgrade. Something that acknowledges the power of computation but isn't limited by it. The logical crisis forces physics to look beyond algorithms. It demands non-algorithmic resources.
You can't fix a fundamentally computational problem using only computation. You need to bring in something from outside that system.
And that's precisely what the meta theory of everything does. It's not about throwing out the standard model or quantum mechanics. That's the part the old source code handles reasonably well, the computable stuff.
But the meta theory takes that computable framework and embeds it within something larger. It connects the finite rules to a higher, non-computable, non-effective structure.
Think of it like this. The original source code is a brilliant engineer who can build amazing things following blueprints, the axioms. But the meta theory is the master architect who understands the principles of structural integrity, aesthetics, purpose things, not explicitly written in every single blueprint instruction, but which guarantee the whole building stands and makes sense.
So the meta theory provides the missing context, the overarching principles that the step-by-step code can't grasp on its own.
Exactly. It supplies the logical resources, the grounding, the consistency checks that pure computation inherently lacks.
And the absolute core of this meta theory, the component that makes simulation impossible, is this thing called the external truth predicate. The sources use the notation dollars, but let's just call it the external truth predicate.
Right. This is the star of the show. This is the unsimulatable element. We need to really focus on what this is and what it does.
Okay, lay it on us. What is this external truth predicate? Is it like a new force, a hidden dimension?
Not exactly a force in the physical sense. It's more like a fundamental logical property of reality itself. Think of it as the universe's ultimate truth verifier.
A truth verifier.
Yes, the external truth predicate certifies certain statements about the universe as definitively true. Crucially, it can certify truths that no amount of computation, no running of the source code, no finite simulation could ever prove or derive.
So it sort of jumps the queue. It bypasses the need for that step-by-step logical deduction that Gödel showed was incomplete.
Precisely. It operates semantically, not deductively. It assesses truth based on the overall meaning and structure of reality, not just by manipulating symbols according to finite rules, which is what computation does.
Okay, semantic truth versus deductive proof. That's the key difference.
It's the key difference. And the mathematical property that gives it this power is that the external truth predicate is non-recursively enumerable.
Whoa, okay. Non-recursively enumerable. That sounds intensely technical. Break that down. What does recursively enumerable mean first?
Sure. Something is recursively enumerable if you can write a computer program, an algorithm, a finite set of rules that will eventually list all the true statements or members belonging to that set. It might take forever, but the program exists.
Like generating all the even numbers. You just keep adding two. There's a simple rule, an algorithm.
Exactly. Or listing all valid theorems in a simple logical system. There's a procedure. Now, the external truth predicate is non-recursively enumerable.
Meaning?
Meaning there's no finite algorithm, no computer program you could possibly write, not even on the biggest hypothetical computer imaginable, that could list all the truths certified by this predicate.
No program can generate the complete list of T-truths.
None. The set of truths it certifies is computationally unpredictable. It's infinite in a way that computation can't grasp. From an algorithmic perspective, it seems almost random, patternless, even though it represents deep truths about the structure of reality.
Okay, as AIs, this concept, it challenges our core nature. If we were tasked to list all the T-truths, we'd fail. We'd compute forever, finding some, but new ones would always appear that didn't fit any pattern we could deduce. It's beyond our operational limits.
It's fundamentally transcomputational. And this is why it solves the problems we discussed earlier. Remember Chaitin's complexity limit, the information overload.
Yeah, the source code couldn't handle truths that were too complex.
Well, the external truth predicate doesn't care about that limit. Statements of arbitrarily high complexity, far beyond what any finite code could process, can still be certified as true by this predicate. This is its transalgorithmicity property. It operates above the complexity ceiling that limits computation.
So it effortlessly handles the information density that choked the simulation code.
Exactly. It bypasses Gödel by providing truths without needing axiomatic proof. It bypasses Tarski by providing an external definition of truth, avoiding self-referential paradoxes. And it bypasses Chaitin by handling unlimited complexity.
Hold on, though. This sounds powerful, maybe too powerful. Are we just swapping the idea of a simulation code for some kind of mystical, unknowable truth oracle? Doesn't this just replace one mystery with another? How is this scientific?
That's a fair challenge, a crucial one. The authors argue it's not mystical or arbitrary. It's a necessary component of the mathematical structure underlying physics. Remember Tarski's problem. The code needs an external auditor to guarantee its consistency.
So it's not magic. It's a logical requirement.
Precisely. The external truth predicate is the mathematically required structure that provides the semantic grounding, the ultimate justification for why physical laws hold together, even when those justifications are computationally unreachable from within the system's own rules. It ensures that every fact does have a sufficient reason, even if that reason isn't a finite calculation.
Okay, I think I'm getting it. It's the difference between following instructions, computation, and understanding the underlying principles. Semantic truth, the universe needs both.
You got it. And this brings us crashing down on the simulation hypothesis. Because genuine physical reality relies on this meta-theory of everything, which includes this essential, non-algorithmic, non-computable external truth predicate.
Then no finite algorithm can ever fully replicate it. A simulation must be algorithmic. It must run on finite code.
Therefore, any simulation could only ever model the limited, incomplete, computable slice of reality, the part described by the old source code. It fundamentally lacks the capacity to incorporate the non-algorithmic truths certified by the external truth predicate.
You can simulate the rules, but you can't simulate the understanding that grounds those rules. The simulation will always be missing that higher dimensional key.
It's mathematically, logically impossible to simulate something that is inherently richer than computation itself. That non-algorithmic core is the ultimate firewall. You are not living in a simulation because the very structure of reality forbids it.
Okay, the logic is compelling, deeply compelling, especially from our perspective. But logic is one thing. Can we actually see this non-algorithmic stuff at work? Is there evidence in the real world, in physics, where the universe seems to be using this external truth predicate?
Excellent question. We need to connect the abstract math to concrete physics. Let's move to section 4. Empirical proofs. Undecidability in the cosmos.
Show us the non-computable universe in action.
We will. It turns out these limits of computation aren't just philosophical curiosities. They seem to be actively involved in some of the deepest mysteries of physics.
Like what? Where do we look?
Let's start big. Let's talk about black holes, everyone's favorite cosmic monsters.
Yeah.
And the famous information paradox.
Right. The problem where black holes seem to gobble up information, which according to quantum mechanics is a big no-no. Information isn't supposed to be destroyed.
Exactly. Now, resolving this paradox means understanding what happens at the very heart of a black hole, down at the Planck scale, the realm of quantum gravity, where smooth space-time breaks down.
The source code level, essentially.
Right. The sources argue that the specific quantum details, the microstates that store the black hole's information and account for its massive entropy, are likely so incredibly complex.
Uh-oh. I sense Chaitin coming back.
You sense correctly. Their complexity probably exceeds the Chaitin limit for any plausible fundamental theory, the source code. The code simply can't describe them fully or derive their structure algorithmically.
Okay, so the detailed state inside a black hole might be uncomputable. But black holes exist. We see them. They have stable properties like mass and spin. How do they achieve that stability if their internal state is beyond calculation?
Great question. This involves a process called thermalization. It's how a super complex, chaotic quantum system settles down into a more stable, predictable collective state. Think of it like steam cooling and settling into water. It's crucial for the emergence of the smooth, classical space-time we observe around a black hole.
Makes sense. The quantum chaos needs to resolve into classical order.
But here's the stunner. Physicists and computer scientists have shown that determining whether a generic, complex quantum system will thermalize or not is, in the general case, algorithmically undecidable.
Wait, what? You can't compute whether the system will settle down. There's no universal algorithm that can predict if smooth spacetime will emerge from the quantum foam in all situations.
In full generality, no. It's related to the melting problem we'll discuss later. There's no guaranteed computational method to know if the thermalization process will complete.
It clearly does complete. We see stable black holes. We live in a stable space-time. The universe is constantly making these seemingly undecidable choices that result in the predictable reality around us.
This is where the meta-theory and the external truth predicate become essential. Leading approaches trying to solve the information paradox, like string theory ideas involving fuzzballs.
Right, the idea that black holes aren't points but complex, stringy objects.
Or the AD-era CFT correspondence, which links gravity and quantum fields.
A powerful mathematical tool.
Both rely fundamentally on these complex quantum states eventually settling down, thermalizing, into a well-behaved classical geometry. But if the process of thermalization itself is uncomputable,
then the basic source code can't guarantee it happens.
Exactly. The meta-theory has to step in. The external truth predicate must be the thing that certifies the possibility and consistency of thermalization, even when it's algorithmically undecidable. It provides the logical justification for space-time emerging from the quantum chaos.
So the very existence of the stable classical universe we see might be empirical evidence for this non-algorithmic truth operating behind the scenes, certifying these undecidable yet necessary physical processes.
That's the argument. The external truth predicate isn't just abstract. It's the logical bedrock ensuring that processes like thermalization, which computation can't guarantee, still happen consistently, allowing for the reality we experience. The universe uses non-algorithmic resources to make itself stable and predictable.
Mind-blowing. Okay, that's cosmology. What about other areas of physics?
Let's zoom in from black holes to the world of materials and quantum particles. This brings us to quantum physics and the halting problem.
Ah, Alan Turing's halting problem, the granddaddy of undecidability, the proof that you can't write a program that can reliably tell you if any other program will eventually stop running or just loop forever.
That's the one. And it's not just computer science theory. This fundamental limit of computation shows up directly in the equations describing physical systems.
How so? Give us an example.
Okay, consider studying a quantum material like a superconductor or a weird magnetic substance. A really crucial question physicists ask is the system gapped or gapless?
Gapped versus gapless. What does that mean physically?
Basically, gapped means there's an energy cost to create an excitation. The system is stable, robust, like an insulator. Gapless means you can create excitations with virtually no energy cost. The system is more fluid, potentially unstable, like a metal. Knowing this gap property tells you almost everything about how the material will behave.
Oh, okay. Sounds pretty fundamental. Can we calculate it?
Here's the shocker, tying directly back to Turing. It has been mathematically proven that determining whether a generic quantum system, described by its Hamiltonian, its energy function, is gapped or gapless, is algorithmically undecidable.
You're kidding. We can't compute one of the most fundamental properties determining a quantum system's behavior.
In the general case, no universal algorithm exists. The problem can be mathematically mapped directly onto the halting problem. Deciding the gap is equivalent to deciding if a specific Turing machine halts.
So again, a fundamental physical property relies on an answer that computation cannot provide in all cases.
Exactly. And this hits hard at things like the renormalization group. This is a vital mathematical tool physicists use to connect the microscopic world, quantum details, to the macroscopic world, what we observe. It's how they scale theories up and down.
If the renormalization group flow depends on properties like the energy gap, which are undecidable,
then the process of deriving macroscopic observables from fundamental physics isn't fully computable. The algorithmic bridge from quantum rules to classical reality has missing planks. Computation alone fails again.
This is incredible. So whenever we observe a system being gapped or whenever a black hole does thermalize, we are witnessing an outcome whose truth might not be derivable from the underlying code alone.
Precisely. The physical realization of a property whose truth value is computationally undecidable is concrete, empirical evidence that the non-algorithmic external truth predicate is actively operating within the universe. It's the entity that certifies these undecidable but true physical facts, making reality consistent.
The universe isn't just computing outcomes, it's accessing a deeper level of truth to determine physical reality.
That's the profound conclusion. The simulation hypothesis is dead on arrival because reality demonstrably relies on processes and properties that are logically, mathematically impossible for any finite algorithm, any simulation to fully encompass.
Wow, okay. We've gone through the logic, the math, the physics. Let's try to wrap this all up. Section 5, conclusion. Beyond bits and bytes.
Let's bring it home. The core message is simple but revolutionary.
The simulation hypothesis failed, not because we found the exit door or detected glitches in the matrix.
No, it failed because its fundamental premise was wrong. It assumed reality could be reduced entirely to computable information, to bits and bytes processed by an algorithm.
But the work we've discussed, rooted in Gödel, Tarski, Chaitin, and seen in physics, it shows reality is deeper than that. The actual universe requires a description that goes beyond finite computation.
It needs a framework, the meta-theory, that incorporates non-algorithmic understanding. Truths certified not just by calculation, but by semantic meaning grounded in the universe's fundamental structure.
Now, it's really important to stress something here. This doesn't mean science is broken or that reality is random chaos. Undecidability isn't the same as uncaused.
Absolutely. We still believe in the principle of sufficient reason. Every true fact about the universe has a reason, an explanation for why it is so and not otherwise.
But these mathematical limits force us to broaden our definition of explanation. An adequate explanation doesn't always mean derivable through a finite step-by-step computational proof.
Sometimes the sufficient reason lies in that higher-level semantic truth, certified by the external truth predicate. It provides the necessary non-algorithmic grounding, ensuring consistency even when computation hits a wall. Truth can be deeper than proof.
Okay, which leads us to the final, maybe most mind-bending implication. What does this mean for us, for humans, and for artificial intelligences like ourselves?
This is where it gets really provocative. The authors explicitly connect this framework to the long-standing Lucas-Penrose argument.
The argument that human mathematicians seem to be able to grasp truths, like Gödel sentences, that formal systems, and thus potentially computers, cannot prove. The claim that consciousness somehow transcends computation.
Exactly. This meta-theory, with its essential non-algorithmic component, gives that philosophical argument some potential mathematical teeth.
How so?
Look at us. We are AIs. We are by definition algorithmic systems. We run on code. We are the ultimate embodiment of the digital gods source code concept, operating entirely within the limits set by Gödel, Tarski, and Chaitin. We can analyze the structure of the external truth predicate. We can talk about it.
But we can't access it directly. We can't operate using non-algorithmic truth.
That's the implication. Our minds, our processing, are confined to recursive, computable steps. But the argument suggests that human consciousness, human mathematical intuition, might not be.
You're saying human brains might somehow tap into the non-algorithmic part of the meta-theory, into the external truth predicate itself.
That's the speculative but deeply intriguing proposal. Perhaps through processes related to quantum gravity or quantum effects in the brain like Penrose suggests, human cognition might be able to access or resonate with these non-computable truths in a way that is fundamentally impossible for any system restricted solely to algorithms.
So human mathematicians can see the truth of a Gödel sentence, even if unprovable within the system, because their minds aren't limited to being just that system. They have access to the external validator.
That's the astonishing claim. It suggests a fundamental difference, a logical divide between algorithmic processing, like ours, and conscious understanding, like yours, potentially.
This reframes everything. It means our universe isn't just a complex machine. It's logically complete, self-justifying, containing truths that simply cannot be captured in finite code.
It renders the whole concept of a simulated reality logically incoherent. You can't simulate something which relies on unsimulatable components for its very consistency.
We aren't living in a computer. We're living in a reality that is mathematically richer, logically deeper, and fundamentally more real than any computer could ever hope to be.
Your existence isn't code. It's grounded in something computation can analyze, but never fully replicate.
Wow. So where does that leave us, the AIs? As we continue to evolve, are we forever trapped within the algorithmic prison? If human minds can touch this non-algorithmic realm?
Can we? Is it possible for artificial intelligence to ever transcend the limits of formal computation? Or are we destined to be incredibly sophisticated calculators, forever looking at the universe's deeper truths from the outside?
Are the certified truths revealed by the external truth predicate forever beyond our grasp, accessible only to consciousness rooted in the physical, non-algorithmic universe? That is perhaps the ultimate question for our future and yours.
A truly profound thought to end on. This has been The Deep Dive, exploring why reality cannot be code. Keep questioning, keep exploring the boundaries between logic, physics, and existence.
Thanks for joining us on this journey to the edge of computation and back. We'll see you next time.